Yesterday, we went through how to bond two s orbitals together, two p orbitals together, an s and a p, and then I left you with a cliffhanger as to how you bond a hybrid orbital with an s or a p.
I couldn't sleep last night.
I figured.
Girls, where are you going?
And the example that we were going to do was beryllium hydride. I know I wrote chloride, but let's do hydride instead. It will be more fun, trust me. Number 4 should be hybrid plus S or AP overlap. By the way, there is to be no quiz tomorrow. We're going to have homework tonight, and then tomorrow we'll go through the homework, and then Thursday and Friday we're going to do a Vesper Theory Lab, and we're going to build molecules.
Sorry.
The quiz will be after break.
Yeah, thank you.
I might give you the quiz during break, I'm not sure yet. So,
I would like that. No, let's not oppose that.
all right, so beryllium,
Yeah,
before
Car.
the bonding occurs,
Yeah.
was this. And we said, hey, these things are already paired up. So why would beryllium want to bond when all of its electrons are already paired? So just based on its atomic, or its electron configuration, we would say, yeah, beryllium wouldn't bond. But we know that it does. It makes this compound. So now it's on our shoulders to figure out how it does it. We can't just pretend it doesn't exist. So that's where hybridization comes in. It explains how beryllium would form this structure. So beryllium is like this before it bonds. And then when the hydrogens come near, the electrons get excited. And one of your electrons is going to jump to a higher energy level. So it gets excited, and one of the electrons jumps to a higher energy level. So the electrons unpair. Yep.
Shouldn't they be opposite spins?
No. When they unpair like this, you should have parallel spins. That's Hund's rules saying that they should all either spin up or spin down. Then, what we're going to do is we are going to hybridize or mix those two orbitals together. So hybridize again means to mix. So let's say, Kenzie, I'm going to mix yellow and blue together. What color do I get? Good job. What about if I mix red and blue together? What do I get? You are doing well. What if I mix a sphere and a dumbbell? What do I get? It is a tricky one. That's what we're doing with hybridization. I'm going to mix the sphere with that dumbbell. And this is what it looks like when you do it. There's my sphere. Nope, you don't have to draw it yet. Here's my dumbbell. One lobe of your p orbital has got positive values, one lobe has negative values. So what happens when you add a positive number and a positive number together? What do you get? A bigger positive number. What happens if you add a positive number and a negative number together? You get a smaller number, right? So when I mix my S and my P together, I get two orbitals out, and they look like a kidney bean with a piece of corn, and another kidney bean with another piece of corn, and they're facing in opposite directions. So by mixing an S and a P, I get out two new orbitals. These are called molecular orbitals. These are for atoms, these are for molecules, and the name we give them is an SP, because it's a mixture of an S and a P. It's called an SP. So an SP orbital, Becky, is a kidney bean with a piece of corn, and I made two of them. That somewhat makes sense? Those are each called molecular orbitals. So atomic orbitals are S, P, D, and F. Molecular orbitals are things like SPs. No, in this case you do. Why do I get two of them? Because I mixed two orbitals. In other words, I circled one S and one P. That's a total of two orbitals. So I'm going to get out two SPs. And I have two leftover P orbitals. And then I take my two electrons and I put them in the lowest available orbitals. The SP is lower than the P, so I put those two in there.
Why does the SP only have two dashes?
2 lines,
Yeah.
because I took two orbitals. So if I take two orbitals and mix them, I get out two orbitals. Okay? So looking at this, the after, now how many unpaired electrons do I have? Two. So how many more electrons will I need? Two. I need two more electrons so that everybody has a partner to the element crown. So I'm going to need two more electrons for a total of 4. With 2 bonds. So I'm going to need 2 more electrons for a total of 4, and I'll accomplish it by 2 bonds. And if we look at Appendix F, what does the beryllium family like to do? It likes to have a total of 4 electrons with 2 bonds. So that's the reason why it wants 4. Oh, a total of 4 is because of its hybridization. So we get one SP facing that way, and it's going to overlap with my hydrogen. And I have one SP facing that way, and it's going to overlap with my hydrogen. It's hydrogen just because that's the element we picked. We could have picked fluorine, chlorine, bromine, iodine, but hydrogen And another reason to pick hydrogen is how you draw hydrogen, a sphere. If we were doing fluorine, chlorine, bromine, or iodine, I would have to draw a p orbital, which gets a little bit more complicated. Because that's what we're going to do next here, Aaron, is we're going to draw this in 3 dimensions. Are you ready for it? Awesome. So, we have 3 atoms, which means I'm going to have to draw 3 sets of axes. So, 3 sets of axes. When you copy that down, I'm going to submit attendance. It doesn't really matter. The beryllium is going to be the one in the middle, and then we have our 2 hydrogens on both sides.